and then after this point, we'll be at a point where you can do the homework, because we're going to talk about kernels and null spaces and rank and nullity and things that you're asked for on the assignment 5. Okay. So it repeats the idea of a linear map here. And it gives you some examples of maps that are linear but not one-to-one. Okay. And then we want to look, what are some consequences just of linearity? One of which is a linear map by itself. It doesn't have to be one-to-one maps the zero vector to the zero vector. And here's the linear map test. F is a linear map. And here's the consequence here. And here is the big consequence of meaning the consequence is the image of a linear combination is the same linear combination of the images of a bunch of vectors. Okay, so, and you can verify but here is some new stuff, okay? Here's we have that section repeats the definition of a linear map, but here's something that's new. Up to this point, we've specified, like if you want to specify a map between, say, R3 to R2, I could say, okay, well, F is given by X, Y, Z. This is what I call the general formula in the assignments and just in general. Okay, we have to give it, we have a three-dimensional vector here that has to go, for example, X plus Y plus Z, X plus 2Y plus 3Z. Okay, so this is going to turn out to be a linear map because, and you can tell it's a linear map because the entries here are linear combinations of the entries over here. If I had like X plus Y plus Z plus 5, it wouldn't be a linear map. Okay, now we can go through and check that. And that's one task, is to check that a given map is linear. What we want to do is show that we can specify linear map in a different way. Okay, here's something that's new. This is this is sort of path 1. This is going to be path 2. The action, this is the new thing. The action of a linear map on a basis specifies the linear map. So I can give you a linear map, if I could spell here, specifies the linear map. What this means is, if I give you the action of F on a basis of R3, you can reconstruct this map here. Okay? I can start here, I can start with 1 and get 2, or start with 2 and get 1. Okay, what do I mean by the action of a basis here? Let's say I have the same thing of G. We'll start from here and find this, but first I want to show you how you specify. Let's say that I have X, Y, and Z, but I don't right away. What I'm going to give you is, I'm going to give you a basic, say R3C to R2C, and I'm going to say, okay, G maps 1, let's take the standard basis, maps 1, 0, 0 to 1, 2, 3. And it maps 0, 1, 0 to 1, 1, 1. And it maps 0, 0, 1 to say 1, 1, 0. Okay? That's when this is a basis action. Okay. So all I've specified, I say, okay, G is going to be a linear map that maps these three things. 1, 0. So I've got the image of the basis vectors, right? Now these can be linearly dependent. These don't. We don't. In fact, actually, what I've done is here, this is supposed to be R2. So let's just chop off the bottom one here and the top one here. Because it's supposed to be R2, not R. I mean, that would be a map from R3 to R. But this is a basis action, right? R3 to here. Okay. Now, you know, one thing you know right away is R2 is two-dimensional, right? Its basis would only have two vectors. So these vectors here can't be linearly independent. They're not going to, because there's too many of them. But it's still, G is still a linear map, but it's not going to be one-to-one. Because it's going to map. Okay, we'll see that later on. But okay, so let's see the idea here. This is a basis action. What's the general formula? That's what I could ask you. Say, what's the general formula for G? What you do is you say, okay, well, G is supposed to map X, Y, and Z to something. Right? We want to know what this happened. We want to know what this is in terms of some two vector with X, Y's, and Z's in them. But we just know this. What we can do is, because we've got the images of the basis vectors, we can say this map here equals X times 1, 0, 0, plus Y times 0, 1, 0, plus Z times 0, 0, 1, right? Then I can say, well, what is G of this vector? Well, because G is supposed to be linear, right? I know this is equal to X times G of 1, 0, 0, plus G plus. Let me write this with different, a little bit different notation. So it's going to be G square bracket of 1, 0, just so that the parentheses don't make it hard to look at, plus Y times G of 0, 1, 0, plus Z times G of 0, 0, 1. Okay, you were saying this is due to G is linear. Shruti, or
that's a problem.
okay. Now, but the point is, I've given you what G of the three basis vectors are. So I know that it's going to be 1, 2, 1, 1, and 1, 0. So this is going to equal X times 1, 2, plus Y times 1, 1, plus Z times 1, 0, right? 1, 2, 1, 1, and 1, 0. So then I can combine these together. This is going to equal X, 2X, plus Y, Y, plus Z, 0, which equals X plus Y plus Z, X plus Y plus Z, and then 2X plus Y. So I know, so here's the general formula. This same map takes X, Y, and Z to X plus Y plus Z, 2X plus Y. So this is the general formula. So I started from a basis action and found the general formula. And I use linearity. I use the fact of linearity to say, okay, I know, if I know the basis action, I know the action on any vector. So you guys okay with this? Okay, well, we can go the other way. Like this one here was X plus Y plus Z, X plus 2 Y plus 3Z. Let's look and see if we can get the basis action. Get basis action from general formula. So I'm going to repeat F of X, Y, Z goes to X plus Y plus Z, X plus 2Y plus 3Z, right? So what I just do is I take special cases. Well, what does 1, 0, 0 go to? Well, that's X is 1, Y is 0, Z is 0. So that's just going to be 1, 1, right? Because Y and Z are 0. then I use the same formula to do, so what's 0, 1, 0 go to? Well, y is the only one that's not 0, so this is going to go to 1, 2, because x and z are 0. And then I can do the third one, 0, 0, 1 goes to, when only z is that's going to go to 1, 3. So I've got the images under F of on the three basis vectors by just doing special cases of the general formula. So I can go back and forth between general formula or basis action. And that's really important because the bases tell you a lot of stuff about the map. Okay, so in some sense, it may look like you've got lots of different maps, but you really just have different basis actions. So that means the linear maps are completely constrained by like here, by certain pieces of information that aren't just big. You can't just sort of, if you write down some general map, it's going to have a simple form as an action on the basis elements. And that's what goes here. If V is a vector space with this basis, and W is any vector space, given any vectors, n vectors in W, see, we can choose any n vectors in W, and there exists a linear map of mapping the vectors in V to those W's. So I can just choose, if I've got a vector space V with, say, 10 vectors, and I have a vector space W, I could choose, W could be any vector space. I can just choose 10 vectors in there and then map, the first map beta 1 to W1, beta 2 to W2, beta n to Wn, and I've got a basis action, so I've got a linear map. So I just have to choose, if I have say a 5-dimensional vector space here, I just have to choose 5 vectors in any vector space, and I've got a linear map. Okay, so that's this sort of power of looking at this stuff. Yeah, this is sort of the theorem that sort of tells you why this always works. Okay, here's a terminology thing. A linear map for a vector space to itself is called a linear transformation, because it's sort of like, if you think, well, if you think of it as a basis action, it's a linear map sort of is taking every vector in space to another vector. It's sort of like, one possibility would be a rotation. I take a space, I take every vector, and I rotate it by 30 degrees. That would be a linear transformation. Okay, so rotations, like if I had a graphic image and I wanted to rotate it or do some kind of graphic transformation to it, that's going to be a linear transformation, which is it's a special case of a linear map. So everything we've done this is just a special case where the codomain is the same as the domain. But and what's going to turn out is that these are cases of, let me not get ahead of myself too much. Okay. There's lots of cases where you have, like the derivative map. If I take the derivatives of polynomials, that's a linear map. Integrals are also a linear map when I take it on spaces of polynomials. Anyway, there's a whole connection to other cases here. So I told you earlier, last time, that, and this is maybe will be a good place to, let me just